Data flow diagram techniques is a modeling techniques for the specification of tasks, specification of processes, and is for requirement analysis purpose. These techniques cannot be used for design. Okay. So yesterday we have already learned part of data flow diagram techniques. Okay. When we apply data flow diagram techniques, firstly, we will construct a set of data flow diagrams. We have learned that yesterday. But that is not all. When we apply data flow diagram techniques, in addition to the data flow diagram, we have to create a data dictionary also. Okay. So after you draw the data flow diagram, we need to create a data dictionary to define all the data flow and data store. Okay. And also to define, to specify each lowest level process. So data dictionary will have two parts. Data and process specification. These are the two parts in a data dictionary. So the first part, data specification, is for us to specify all the data flow and data store. Okay. So if we will give a data specification to each and every data flow and data store under this component. And for processes, we only need to give a specification to each lowest level process. So once you have given a specification to each lowest level process, and together with the data flow diagrams, okay, all the processes are specified. Okay, first, so we are going to, from this slide onward, we are going to learn how to specify data flow and data store first. Then after that, we will take a quick look of how to specify each lowest level process. Okay. For data flow and data store, okay, we will create a data specification for each of them. Okay. So once we have a set of data flow diagram, we will define a data specification for each data flow and data store. How to define data specification for each and every data flow and data store? Okay, very simple. We will define each lowest level, we will define each data flow and data store by showing the data item it contains, by showing the composition from data items. How to show a composition of data flow and data store by data items? Okay. We use 4 basic structures to show them: sequence, iterate, option, optional, and case. I'm going to illustrate to you how to define data flow and data store using these 4 basic control structure to show how each data flow and data store, okay, in terms of the composition of data items. Sequence, okay. From the word, it implies that sequence means sequentially combine other items together. Okay. So the notation for specifying sequence is plus. We use a plus sign. Okay. How to define sequence? This is the way to show sequence. Okay. If a particular data item is the combination of two lower level data item A and B, okay, A appears first before B, then this is the way to define sequence. Sequence, that means combine together in the sequence shown. So A plus B means this particular data item is the combination of two lower level data item, that is A and B. A comes first, then before B. Okay, example is here. Okay, name. Our name, most of our name here have a surname, then after that follow with other names. Okay, so we can define name equal to surname plus other name. That means our name will be surname first, then follow with other name. Iterate. Iterate is to show combination of values. Okay. This is the notation to show the iteration. Iterate, curly bracket with the asterisk here on top. Okay, if we want to show that a particular data item is the combination of a number of values of A together. Okay, so a particular data item is a combination of lower level data items A, combination of the number of value of data item A. Then this is the way to show it. We put A in the curly bracket. Okay, this is to show that this particular data is the combination of multiple value of A. There's an example here. Okay, in a company, employee, in general, an employee may hold many appointments in the past. So the past appointments is actually can be defined by appointments. Past appointments is the combination of number of appointments. All those appointments the employee hold in the past. Okay, so this is the way to use iterate. Optional. Optional is to show that a particular data item is formed by either a value of A or do not have any value at all. So that means over here, A is optional. A may have a value, okay, for this particular data, okay, it may have a value of A, it may not have any value at all. So we have a rounded bracket to show that it's differentiated from the curly bracket. That is to show iterate. Here there's example, employee particulars. We can define employee particulars equal to this part, I didn't write it down. Name, address, etc. Okay? Employee number, I didn't write it down, I put ... Then, each employee may have a car number. Car number is optional. Those employees have a car, we have a car number. Those do not have car, we don't have car number. So that's why I put it in a rounded bracket. Then plus some more things, plus some more particulars of employee. This is the way to define optional. Okay, case, last structure. For case, we use vertical bracket, another kind of bracket. So separated by vertical bar. Case means these particular data items, this particular data, okay, either have a value of A or B or C, have one of them, only have one of them. Here, although this example I show you 3 cases, it can have many cases. It depends on the requirement. It depends on what you want to describe. Okay, here there's an example. Personal identification. In general, personal identification is either IC number or FIN number. So this is the way we identify. This is the way we define personal identification in Singapore. Either IC number or FIN number. Okay, one of them. We not have both. So this is the way to showcase. Okay. So how we define data specification? All the data flow and data store in the DFD, we will give a data specification in our data dictionary, okay, by using these 4 basic structures to show their compositions. In terms of the lowest level data item, lowest level data item means in terms of elementary data item. Elementary item means when anybody look at it, straight away, he will know what it means. Don't need any further explanation. So we have defined all the data flow and data store by using these compositions in terms of elementary data items. Next 2 slides will give you an example of how to define a data flow. Okay. We have a partial data flow diagram here. This, I only show a partial data flow diagram is because we want to define a data flow in this diagram, okay, a particular data flow in this diagram. Take for example, place order. Okay, I want to define order, the order produced from place order in this data flow diagram. Of course, this data flow diagram, we have a lot of other processes also, but we just want to use this one as an example to see how to create a data specification for this data flow order. Okay, and the assumption is written now here. Assuming that in this data flow diagram, the order, the data flow order, that is a purchase order, consists of 4 components. Okay, at the higher level, it consists of 4 components, 4 higher level attributes. That is supplier name, date order, method of payment, and order items. Order items. And these are the assumptions here. Okay. Supplier name always have a first name. We assume that every supplier will have first name, then a last name. Definitely we have these 2 data items, every supplier name. And there may be a middle name also. Okay. That means the middle name is optional in the center between first name and last name. And date order, okay, the second part is an elementary item. We assume that date order item is a basic data item, is an elementary data item. That means when anybody look at it, straight away he will know the meaning, he or she will know the meaning. Don't need any further explanation. That's our assumption. So, and that is what I mean elementary data item. So when we use data flow diagram techniques, we will define data flow and data store, okay, using the 4 structure I've explained to you in terms of elementary data items. Okay. So we are going to do this in this example. Okay. Method of payments must be one of the 3 values. Okay. It can be that means there are 3 ways to pay the supplier, either through check, credit card, or money order. These are the 3 options, 3 ways to pay the supplier. Okay, so must pay through one of these methods. Order items. Okay, order item is formed by a number of values of lowest level attribute lower order item. That means order item has many. The meaning of order items here, it means a sequence of 9 items that the company want to purchase from the supplier. And each 9 item we have 2 attributes, item name and quantity order. Okay, these are the assumptions, and this is the part of the data flow diagram that we are going to define data store. Okay. In other words, physically, a supplier order is as such. Supplier name, date order here, then method of payment indicate the method of payment. Then a number of order items here, a number of first item, second item, third item, etc. So how many can be, an order can have 2 items can purchase, 1 item can purchase, 2 items can purchase 10 items together, depending on how many items we want to buy. Okay, so this is the assumption, and the data flow diagram I have already shown you how to define data specification. Okay, this is the way to define data specification. Firstly, we say that order is a combination of these 4 together, these 4 components together: supplier name, date order, method of payments, and the last part is the combination of a number of order items. This is called 1 order item. This is called 2 second order items. So that means supplier orders is formed by these 4 components. Okay. So we use a sequence structure to show that. Okay. Then after that, we will define each component in terms of lowest level data items. Okay, so earlier our assumption said that supplier name may have a first name first, then definitely we have a last name at the end, but middle name is optional, so we define accordingly over here. Okay, so middle name is optional, we put them in a rounded bracket, and method of payment is one of these three: check, credit card, or money order. Okay, so we define accordingly. All these are elementary data items, and order item has two lowest level, have two elementary data items. That is item name and quantity order. So again, we define accordingly and assume that all these are lowest level data items. Okay, are elementary data items. So that means we can stop here. So you can see that the way we define, the way we write our data specification, also using hierarchical decomposition, also using top-down decomposition. That means we will not attempt to define elementary data items straight away. Okay, we can define gradually. You can see that the purpose of this data specification, this set of data specification, is to define order. You can see that initially we do not define order in terms of all elementary data items. Okay, we define them as component first, except this one. Date order is an elementary data items. The rest are not elementary data item. Then after that, we define the detail of each of them until we reach the elementary data items. So the way we do, the concept for creating data specification is also similar to drawing data flow diagram. Okay, we are also using hierarchical decomposition, top-down decomposition. Define it gradually from top to bottom. This is a top level composition. Then after that, we define it. If they are not the elementary data item, we give a specification to them. Okay, if they are, then we will stop. Like date order is the elementary data, so we stop at it. Okay, so that is the way to give a data specification to each and every data flow in your data flow diagram, and we put it in data dictionary. The second part of data dictionary is to define, is to specify each and every lowest level process. These are the various methods that you can use to specify a process. You can use narrative. That means you can specify a process informally by using English in point form, narrative. You can use pseudocode, PDL. Okay, this is the most commonly used method, and I'm sure you have learned that in EE4008, okay, data structure and algorithms. Equation, you can use equation to define a process also. Let's say, for example, if your process is to compute triangle area, then you can use a formula to define it. You can use a formula area equal base times height divided by 2. Use equation to define a process as well. You can use tables. Draw a table to show how output is to be computed. You can use diagram or charts. These are the various methods for specifying process. Okay, and pseudocode is the most commonly used method. And next slide will just give you a refresh of pseudocode. Okay, we will not spend too much time on it because you have already learned that in EE4008, data structure and algorithms. Okay, this is a quick revision of pseudocode. And basically, pseudocode only have more formal syntax for the basic control construct. Okay. And in terms of other statement, that means in terms of action, you can use a simple English to describe. Okay. So only have formal syntax to show the basic control structure. Okay. So over here we have all the basic control structure. I give you an example here. Okay. So this is a piece of pseudocode. Always start with begin and end. And sequence, how to show the basic control structure. There are three types of basic control structure. Sequence, selection, and iteration, in other words. Okay. So this is a begin and this is an end. Okay. So we read X appear first. That means this will be performed first. This action will be carried out first before read Y. Okay. This is the way to show sequence. Select. We use if then else to show select. If certain condition is true, if X greater than Y is true, then this action will be carried out. X, that means X will be defined, X, the value of X will be set to X minus Y. If X greater than Y is not satisfied, if this condition is not true, then those actions written under else branch will be performed. So that means Y will be set to Y minus X. So depending on whether this condition is satisfied. So this is the way to show select using if then else. Iterate, looping, how to show looping. This is the way to show looping in iteration, the yellow color. While condition loop. That means if this condition is satisfied, all the action between while and end loop will be performed. If this condition is not satisfied, okay, this action will not be performed. That means you will go to the next statement after the loop construct, after the iterate construct. That means you will come here. If the condition is not satisfied, you will come here. Okay, that is the way to show iterate. So in pseudocode, beside the controls structure, the rest of the action, okay, can be described by simple English as such. Okay, this is so much on pseudocode. That means now we have learned DFD techniques. In DFD techniques, okay, we will draw a set of data flow diagram. Okay, how many data flow diagrams you will have? It depends on your system, on the complexity of your system. And how many levels you may have for your data flow diagram, it also depends on the complexity of your requirements. Right. So we will have a set of data flow diagram, and we will have a data dictionary. And in your data dictionary, you will have two components. The first component is a data specification for each data flow and data store. Okay, the second component is a process specification for each lowest level process. And usually we will use pseudocode to specify each lowest level process. Okay, so that is data flow diagram techniques, and this techniques is for modeling tasks, modeling processes involved in our systems. Okay, and the earlier techniques that we have learned, ER modeling is for modeling the information. Okay, now we come to the last part of this unit. Okay, the last part of this unit will give you a quick introduction of a methodology for requirement analysis. The two techniques that we have just learned, ER modeling and DFD techniques, are modeling techniques. They are not methodology. Okay, methodology is different from a modeling technique. A methodology will achieve a bigger objective, and a methodology usually will have a number. A methodology usually will include a number of modeling techniques together, okay, to achieve a bigger objective. So the two techniques that modeling technique we have just learned. The ER modeling is for modeling information, and DFD techniques is for modeling the processor's tasks. Okay? And in general, software requirement have two aspects, information and requirement. So you can see that each modeling techniques cover only one aspect for requirement analysis. Okay? It will not achieve the whole purpose of requirement analysis. Because in requirement analysis, we have to, since there are two aspects, we have to deal with both aspects. So, modeling techniques, each of them, we have just learned, the two modeling techniques, each of them address only one aspect. Okay. So the next few slides will give you a quick introduction of a methodology for the whole purpose of requirement analysis. That means we are going to have a quick look of a methodology that will achieve a bigger purpose, the whole requirement analysis. Okay, before I introduce you this methodology, since this methodology is for requirement analysis, so we take a quick look of what is exactly requirement analysis. The objective of requirement analysis is to specify software operational characteristics. Okay. That means the objective of requirement analysis is to specify how the requirement can be achieved conceptually, logically. Conceptually, logically means how to implement the requirements, okay, from user viewpoint without including those information needed for programming purposes. Okay. To show a conceptual implementation. That is the main objective of requirement analysis. Okay. In addition, requirement analysis should indicate all the software interface with other system elements. Okay. If your system need to interact with some other external system, some other foreign systems, okay, then we have to specify them during requirement analysis also. Take for example, NTU personal and payroll system. End of the month we have to generate a payroll and transmit electronically to banking system, for the banking system to credit employee accounts, bank accounts. So such external interaction, with external system, foreign system, banking system, have to be specified during requirement analysis, of personal and payroll systems. Establish constraint. Okay. In addition to external interactions and conceptual implementation, we have to show all the constraints, define all the constraints. Constraint, for example, things like if your systems must have quick response time, must have fast response time, must have 1 minute, 1 second response time. Okay. That must also be specified during requirement analysis. Okay, so these are the objectives for requirement analysis. So requirement analysis basically is for software engineer to elaborate details, on basic requirements, okay, to elaborate all the detail required for the implementation of basic requirements from conceptual viewpoint, from end user viewpoint. So over here, you have to build conceptual model. That means you have the way you specify how a system can be implemented, all will be from user viewpoint. Those data, those structure that you need to incorporate for writing program purposes only should not be included in the conceptual model at this stage. Okay, so briefly, the deliverables, the output we create during requirement analysis, okay, we call it as analysis model, and that will serve as a bridge between requirement and design specifications. So things like data flow diagrams, things like ER modeling, those you are going to create for requirement analysis, it serves as a bridge for you to move from user requirement to design, in other words. Okay, here, this slide, there are some rules of thumb that we should follow for requirement analysis. Okay, I will not go through each of them. Most of the items here I have already covered. Okay, I will highlight one more important point. This is the more important point. Minimize coupling throughout the systems. Okay, so that means when we do requirement analysis, when we specify conceptual implementation of a systems, we should minimize coupling between parts. Take, for example, when you draw a data flow diagram, okay, the way you divide a higher level process into sub-processors, you should divide them in such a way that between sub-processors, okay, they have minimum interdependency. Okay. They should not depend on each other too much. They should have minimum interdependency. Definitely, they will have some dependency, okay, but we should cut down dependency to the minimum. That is coupling. Okay. The interdependence between parts. When you apply data flow diagram, parts are processors. When you decompose a higher level process into sub-processors, you should try to minimize the interdependency between sub-processors. Okay, now we come to the last slide. The last slide is to give you a quick introduction of the methodology, the requirement analysis methodology. In general, there are two types of requirement analysis methodology. Structural analysis are the traditional methodology, and object-oriented analysis. Okay. From next unit onward, we are going to learn object-oriented approach. Okay. That will include object-oriented analysis. Okay. So this slide introduces you structural analysis. That is the traditional methodology for requirement analysis. Okay. So what is structural analysis? Okay. Structural analysis is basically structural analysis is the combination of ER modeling and data flow diagram techniques together, okay, to achieve the whole purpose of requirement analysis. Earlier we said that regardless of how complex a system is, definitely requirement can be classified into two aspects: information, data, and processors. Okay, so that means in requirement analysis we have to deal with both aspects. So in structural analysis, we apply ER modeling to deal with information, to model the data, and we apply data flow diagram techniques to model the tasks, the processors. So by doing so, we deal with both aspects. That means in structural analysis, we use these two techniques to complement each other to achieve the whole purpose of requirement analysis. And we do it separately. We do data modeling and process modeling, that is separately, by using ER modeling and DFD techniques respectively. Okay, so that is all for structural analysis. Okay, now we proceed to Unit 3. Okay, in Unit 3, Unit 4, and Unit 5, we will learn the newer approach, newer modeling techniques for requirement specification, requirement analysis, and design. And the techniques that we are going to learn in these 3 units, okay, is from this language, Unified Modeling Language. In short, we call it as UML, Unified Modeling Language. Okay. The word unify comes from the fact that all the techniques in this language can be used across all the stages for software development. It is not only used for one stage. Okay? It can be used for multiple stages. Can be used, in other words, can be used for requirement specification, requirement analysis, as well as design. It's not restricted to requirement analysis only, like DFD techniques and ER modeling. And this techniques is quite well accepted in the industry as a standard language. It's quite commonly used as a techniques for specifying software problem and solutions. And all the techniques in Unified Modeling Language is also a semi-formal language. I have already explained this term semi-formal before. That means the output they are going to create will contain most of the detail required for system development, but it cannot be automatically processed by machine. That's why I call it semi-formal. And it's graphical-oriented. Okay, most of these techniques are graphical-oriented. That means they are basically very much diagram-based techniques. Okay, so something like what we do before, using diagram, mainly using diagram to for specifying requirement or for specifying design, and they may also use textual specification to supplement it. Okay, so what we are going to learn? We are going to learn the basic techniques in UML. Okay, so all the modeling techniques can be classified into these two types: structural modeling, behavioral modeling. Okay, what is structural modeling? Structural modeling is to model those aspects that are independent of time. It won't change with time. It won't be affected by time. Things like the structural information, things like structural tasks. Okay, all this will not change with time. It does not depend on time. Okay, so this is the first type of modeling techniques. So for structural modeling, we are going to learn class diagram techniques in UML. For behavioral modeling, behavioral modeling is to model those aspects that are dependent on time. So that are totally different aspects. So we are going to learn some techniques for behavioral modeling also. So in Unit 3, we will learn class diagram techniques. That means we will learn structural modeling techniques, the basic structural modeling techniques in UML. And in Unit 4, we are going to learn behavioral modeling techniques. Okay, these are the various behavioral modeling techniques we are going to learn. We are going to learn use case techniques in detail, and we are going to learn state diagram also. And I will quickly introduce you sequence diagram and activity diagram also. For sequence and activity diagram, I will just give you a very quick introduction. Okay, so that means, in other words, in Unit 3, we are going to learn class diagram in quite details. And this is the basic modeling techniques in UML. Okay, class diagram. When we apply class diagram techniques, we will model things in terms of object. Okay, object is the basic concept in class diagram techniques. That means class diagram techniques can be applied to both analysis, requirement analysis, and design. In other words, when we apply class diagram techniques during requirement analysis, we are going to specify the conceptual implementation. We are going to model the requirement in terms of object. And when we move to design, we will model the design in terms of design objects. Class diagram techniques is the extension of ER modeling. Okay. So why we say class diagram techniques is the extension of ER modeling. Okay. In terms of diagram, there are some similarity. Okay. And in ER modeling, when we apply ER modeling, and the objective of ER modeling is only for modeling, for systematically specifying information. But class diagram, okay, go beyond that. Okay. When we use class diagram techniques, we will model information, the structural information and structural tasks together. We no longer focus only on information alone. We will model, we will specify these two things together by using the basic concept of object. Object has many, this concept has many strengths. It can support better software design, and it will also make software more reusable through the object, concept objects. Okay, that's why class diagram techniques based on object. Okay, since object is the basic concept we are going to use in class diagram techniques, so the next two slides will illustrate to you what is object and also give you some example on object. An object basically is an abstraction, okay, of something in a problem or solution, depending on whether you are working on requirement analysis or design. So object basically is an abstraction for us to specify information and tasks together, and the associated tasks together. Tasks mean those tasks that things can perform or can perform on the things. Okay. So object is a concept, is an abstraction for us to specify a type of things, okay, together with the task together with the associated task. Object specify these two things together through two components, state and behavior. Okay. So every object will have state something like a situation, like condition. Okay. Okay. Take for example, in subject registration system, we can model each and every student by using the concept object. You can model each and every student as a student object, and student object will have state. Student is in the first year, second year, third year, fourth, final year, etc. All these are state. And student will have behavior also. Behavior should be things like, okay, student can take exam, can register subject, can register course, and student can also select FYP, final year project, depending on the level of study. Okay, so these are the behavior. That means the task associated with object. So we have these two components. That's why we can use this concept to specify information and task together. Okay. All the information are specified. All the information are combined together to form the state of object, and all the tasks that associated with things are combined together to form the behavior of objects. Okay. So it has these two components, so that's why we can define information and associated tasks together. Okay. So later when we go into the details of class diagram techniques, you can see that we use a set of attributes to describe the state. Okay. Since we have two components, so how to define these two components? We use a set of attributes, okay, to specify the state, because state basically is to define the information things have, and we use a set of operations to describe the behavior of object. That's what we are going to do. And object will interact. We use relationship to show how objects interact with each other. Here we have some example on object. A student can be modeled as an object, okay, and shirt can also be modeled as an object depending on our problem. Okay. And behavior, when we model student as object, these are the behavior. Student can register subject. I have already read up just now. Okay, and these are the possible states. Okay, so the rest I will leave it to you to go through. Okay, specifying object. How to specify object in class diagram techniques? We use a class. In class diagram techniques, we use a class to specify a collection of objects that have identical properties. So when we apply class diagram techniques, we will use the concept of object to represent each and everything that are important to our problem. And we define a class to specify a group of objects that have the same property. Same property here means that since the object has two components, same property means it has the same set of attributes and it has the same set of operation. We put them together. So each object, then when we define a class to specify each and every object that we want to model, then every such object will be an instance of the class, or we call object of the class. Take for example, we can define a student class, okay, a class called student to specify each and every student. Okay. Once we define such a class, each of you is an instance of the student class. Each of you is also called an object of the student class. We can define a lecturer class. So once we define a lecturer class, myself is an instance of the lecturer class, etc. Okay? And in a class, we will specify attribute and we will specify operation. The operation can also be called as method. Equal to method means operation can also call as method. Okay. Before we proceed to the notation, let's take a quick look of some example. Okay. Because by now we have already gone through a few basic concepts: class, object, attribute, and operation. So how to use this concept to specify things in real world? Class is to model a types of things in our problem. Okay, if we do subject registration system, a types of things will be lecturer, student. So we can define class to specify all the lecturers. We can define class student to specify each and every student. Object. Okay. Object is to model an instance or a piece of things. So things like IBM is a specific individual supplier. We should model it as object. Under class diagram techniques, Michael Lee is an individual student. That should be modeled as object. Attribute. Okay. Attribute is to model a property of a types of things. Things like supplier name. Okay, supplier name is a property of suppliers, of all the suppliers. So that should be modeled as attribute. Student address is a property of students in general. So that should be modeled as attribute. Operation. Operation is to model, to specify associated tasks. Things like compute interest, draw, and circle. All this should be modeled as operation. Okay, now we come to a notation. These are the notation to define class. We use a rectangle to specify a class. Okay. In class diagram techniques, the name you want to give to the class is written in the first region. The rectangle is divided into three regions. The first region is to show class name. The second region is to define all the attributes of the class. The third region is to define all the operation, because object, we use a set of attributes to define information of object, and we use a set of operation to define the task associated with object. So attribute will be defined in the second region, and operation will be defined in the third region. And this is the format to define attribute. We list them down one after another sequentially. Okay, this is the first attribute, this is the second attribute, and you can define, you can specify data type, whether it's integer or string, etc., and equal to default value. That means if no value is entered, whether you want to set to a specific spatial value or not, if you want, then you will define a default value here. So this is the format to define an attribute, and this is the format to define operation. Okay, operation, similarly, operation, you will get operation name first, then put the argument list in a bracket, then full colon. After that, you have a result type. Result type. That means If the operation return a value, you will show the data type here. If this operation return a value, you will show data type here. If the operation do not return any value, just change some attribute value of object, then we will not have result type. Okay. So here is a simple example. Okay. This is a very simple example. Over here, you can see that I do not define data type for attribute. I do not define default value for attribute as well. Okay. And for the third region is to show all the operation. Over here, I do not show the argument list. I do not show the result type. Also, how much you have to include depend on what information you have. Okay. If you do not have information, we will just skip them. Okay. That is the way we construct class diagram. Okay. So we define this person class to model to specify each and every person. So my cell is an instance of this class, and your cell is also an instance of this class. Okay. A person can change job, person can change address. That's why we have these two operations here. Okay. This is the simplest example. We have a more complete example here. Okay. Also to define person class. So here for attribute, name, person name. Okay. First attribute. Then I have a full colon here. After that I put a string. That means the data type for name is a string. Okay, everybody will have a string as the name. And put the equal, open inverted, close inverted. That means when the name is not entered, it will be set to blank. It will be set default value. Okay, I define default value here. Then follow with some others attribute. For operation, change address. Okay, here I define the argument list. Okay, so put bracket. I have a bracket. Inside bracket there are something here. I have two parts here. The first part, strict name. I put a full colon string. That means the first argument for this operation is the strict name. And strict name is the data type. Strict name is string. Then I have a semicolon. Semicolon is to separate arguments. Okay. Operation may receive 2 arguments, 3 arguments, or even 10 arguments, depending on the operation. Okay, so here we have 2 arguments. So we use semicolon to separate arguments. And this is the way to define, to specify argument list. And after the bracket, I do not have full colon, I do not have other information. That means this operation do not return any value. That's why there's no result type specified here. For the second operation, get name, okay, I have empty bracket. Empty bracket means that this operation will not have any argument. Do not have any argument. That means it will not, this operation does not expect any input, and by performing this operation, it will return a value. The type of return value is string. So that's why I put a string here. So this is the way to define result type. Okay. So today we will stop here. See you again next week. Okay. Another point I forget to mention. The quiz. The tutorial solution. By the end of the week, I will post it to the course website. So you need not to take note when you attend tutorial class. Just pay attention. You need not to take notes, and you need not to take picture. After Friday, I will post the tutorial solution to the course website, so you can print a copy from there.